This is an introduction to Rosemary Ainsley's circuit. In January 1999, Rosemary Ainsley, who is a scientist in South Africa, made a patent application for a device which has 17 times more power output than its own input power. I personally was never in any doubt that Rosemary Ainsley would encounter fanatical opposition to her scientific paper, because scientists, for want of a better word, are unwilling to accept her simple system with vastly more power output than the power input. Rosemary Ainsley has produced a pulsing oscillator system which has been measured at a performance of COP equals 17, that is, a coefficient of performance of 17, which means that the output power is 17 times greater than the circuit's input power. As far as I am aware, this has not yet been replicated by other people. The Panacea BOCAF organization people are working to produce an independent implementation of the circuit. At this point in time, the heater has been built to a prototype testing scale for laboratory examination and measurement, and that has not been produced yet in a kilowatt range, which hopefully will come at a later date. The meaning of laboratory examination and so on is that the power output levels of the circuit that has been developed and tested are low. We're talking about 50 milliwatts or so in the level of a power measurement. Rosemary arranged her circuit to operate a heating element because scientists like her find it convenient to make reliable power comparisons based on heat measurements. The Panacea BOCAF people have produced a 250-page document describing the research, the testing, the theory and so on, and that document can be downloaded free using this particular link here. The document contains the details which scientists need to see for serious testing and development. It may be a little technical for some people. This here is Rosemary's circuit. As you can see, there's a 555 timer chip driving a field effect transistor, which is an IRF PG50 type, and there are 3 fairly fancy variable resistors, one marked gate, one marked off, and one marked on. The connections for a 555 chip are shown here, and the connections for an IRFP G50 FET are shown there. The components are actually listed in this table. In very broad outline, the circuit produces the same very short, very sharp voltage pulses that are the basis for so many free energy devices. The circuit used looks very simple, but in spite of looking simple, the way that it operates is not at all simple. To a quick glance, the circuit looks like a standard 555 timer chip used in many existing applications. However, if the circuit is operated as a 555 pulsing circuit, then the output power will definitely not be greater than the input power. That is, the coefficient of performance will be less than 1. Looking more closely, you notice that the link between the output of the 555 chip on pin 3 and the input gate of the field effect transistor is unusual in that it's not a normal voltage divider. It's just a straight connection from pin 3 through a variable resistor directly into the gate of the field effect transistor. The 555 chip shown in this circuit is an NE555N chip. Many 555 chips struggle to reach 50,000 cycles per second. To get the circuit into its coefficient of performance greater than 1 operation, the resistor marked gate is adjusted very slowly to find the point at which the circuit becomes unstable, overrides the normal operation of the 555 chip, and starts oscillating at the resonant frequency of the overall circuit, forcing the 555 chip to become a feedback component. The circuit then produces the sharp, short voltage spikes at more than 10 times the operating speed of the 555 chip, and pulsing the 10 ohm heating element marked load at about 500,000 pulses per second. I'm told that some 555 chips can operate that fast, but many 555 chips definitely can't. The timing elements of the chip should be producing a much lower frequency, as indeed it does before the gate resistor adjustment causes the circuit to break out of its normal design mode operation and start the high-speed spike generating resonant performance, which draws in additional energy from the local environment. Most circuits which draw energy in from the local environment generally need to be tuned to achieve resonant operation. It is also found that a waveform which is rich in harmonics is needed to produce the best results. For example, Ronald Klassen recently produced an analysis of the operation of Bob Boyce's electrolyzer toroidal pulsing. Bob's circuit generates 3 separate waveforms, one at about 42.8 kHz, and 2 harmonics, one at about 21.4 kHz and the other at about 10.7 kHz. Ron examined the operation with the 2 harmonics slaved exactly to the master frequency, and then again with the 2 harmonics free running and not quite synchronized, so that a random pattern of harmonic pulses were generated. Surprisingly, he found that the random arrangement gave much higher gains than the precision circuit. The same sort of situation is found here in the Ainsley circuit, as a very precise adjustment of the gate preset resistor R1 has a major effect on the circuit performance, while the other 2 variable resistors R4 and R7 are used to adjust the frequency of the pulses and the ratio of on time to off time. Like almost every other circuit which produces a greater power output than the input power required to make it operate, very careful adjustment is needed. The characteristics of the load heating element R3 are also very important. With some configurations there is no excess power generated, while with others there is a very marked increase in power, and the prototype apparatus produced power outputs in excess of 4 times the input power. A quick glance at the circuit diagram makes it appear that there is no significant connection between the 555 timer chip and the IR FPG50 FET transistor. This is not the case, as the arrangement as shown generates transients which modify the oscillation of the 555 chip. This is presumably due to the nature of the current draw by the gate of the FET, or through induced currents caused by the pulsing of the inductive load heater coil R3. We tend to think of FET transistors as having next to no current flowing into the gate, but the IRFPG50 can draw up to a massive 6 amps for the gate to source current flow. The NE555N chip supplying the gate current with no current limiting resistor between the 2 devices can supply a maximum of only 200 milliamps, or possibly 300 milliamps at a push, which is only 5% of the possible current draw by the FET. The circuit of the NE55N chip is shown here. That is the circuitry of the device that's being connected as part of the circuit. From this, it appears that the direct coupling of the output could allow some modification of the chip timing and waveform if the output current draw is well above the design value. The internal resistors preventing destruction of the chip and reducing the effect so that it just modifies the functioning of the chip. This is also suggested by the fact that the adjustment of the grid variable resistor, which controls the NE555N current draw, is the most critical adjustment of the circuit. Supporting that idea is the fact that the required chip operation does not take place if the grid resistor setting is too high or too low. Presumably the setting has to be an exact amount so that the specific physical NE555N chip operation is altered to make it generate waveforms not envisaged by the chip designers. The physical separation of the load resistor and the circuit board may be important, as there's almost certainly a magnetic feedback element as well. I'd love to tell you that the circuit operates in the way that the circuit diagram would suggest, with the timing and Marx base values controlled as expected by the 555 chip designers. However, that's definitely not the case. If the 24-volt battery is disconnected, then the NE555 chip section of the circuit performs exactly as expected by the chip manufacturer. If the R1 gate resistor is at the correct setting and the 24-volt battery is then connected, the result is that the normal running of the NE555 chip is overridden and the circuit immediately switches into a completely different type of operation. The Marx base ratio is forced into an approximately 55% setting, and the pulsing rate is bounced to over 500 kHz. This is the waveform generated by the circuit. You will notice that this waveform has repeating pairs of pulses, neither of which is a square wave. The overall circuit is clearly not operating as an NE55 chip circuit any longer, but is oscillating in an unexpected way. This high ratio frequency pulsing produces electromagnetic waves which radiate from the load resistor, an effect which is seen on a nearby television set. This is not really surprising, as the circuit should really be presented like this. You have the timing mechanism for the 555 chip, the direct feed to the FET transistor, and the load is shown here as a coil, which it is. The 10 ohm resistor R3 is actually a coil of wire. The specification for this component shows that it has a length of 150 millimeters, that's 6 inches, a diameter of 32 millimeters, which is 1.25 inches, and is an air core coil wound with 48 turns of resistance wire with a 1 millimeter gap between each turn. The lack of a core allows the coil to oscillate at this very high frequency, and any coil driven at that frequency radiates radio waves. It is almost certain that these electromagnetic waves are inducing voltages in the wiring surrounding the NE555N chip circuit, causing it to run wildly outside its design parameters. The wire-wound adjustment resistors are little coils which have the potential for picking up transmitted waves. This pickup mechanism is strongly supported by the fact that only an NE555N chip will operate in this way, and 3 other makes of 555 chip which were tested failed to produce this runaway action. The higher runaway frequency is important for achieving power gain. Don Smith states that the extra power being drawn into a circuit is proportional to the square of the pulse frequency. If this is correct, then moving the pulse rate up over 500,000 pulses per second will have a major energy effect and explain why tuning the circuit into this high-speed mode is important. The practical method of tuning the circuit into the self-oscillating, non-symmetrical, power-gaining mode is by monitoring the voltage of the V1 24-volt battery. When the circuit is out of tune, the battery voltage gets pulled down quite noticeably. When the circuit is tuned correctly, there is a slight increase in the battery voltage. If the circuit has been built as described, using an NE555N timer chip and a high inductive load resistor coil, then tuning the circuit is performed as follows. Connect a digital voltmeter across the 24 volt power supply and note the exact reading. Set the on preset resistor to its minimum value of 0 ohms. Set the off preset resistor to its maximum value of 10k ohms. These resistors are generally left at these settings throughout. The gate resistor is now adjusted very carefully, watching the voltmeter reading. As the circuit comes to its best possible tuning, the battery voltage will rise. Pick the resistor setting which gives the highest battery reading. The rise in battery voltage is caused by the inflow of external energy. Some of this flows through the load, causing heating effects, which can be 17 times greater than would be normally expected. Part of the inflowing energy flows back into the power supply, and that flow lowers the current draw from the 24 volt battery, which in turn allows it to show a higher voltage reading. This mechanism is exactly the same as is described by Tom Bearden when explaining the operation of John Bedini's battery charging pulse circuits. Part of the extra energy goes into the load and part goes back into the power supply. Although it's not mentioned in the parts list, it is very important to mount the FET transistor on a heatsink, as the current flowing through it causes it to heat up. Also important is to use a mica gasket between the FET and the heatsink. A mica gasket is a thin layer of mica which electrically insulates the FET from the heatsink, while still acting as an extremely good conductor of the FET heat to the heatsink. It is necessary because the drain pin of the FET is connected electrically to the metal mounting strip of the FET, and if the FET is not insulated from the heatsink, then the heatsink acts as a radio aerial and radiates an embarrassingly large level of radio waves. The heatsink can be a simple sheet of aluminium, or it can be a commercial finned design, of which there are many to choose from. A suggested physical layout for this circuit is given towards the end of this document and can be used if you're interested and inclined to do so. This is a circuit which cries out for replication and investigation by both experienced and inexperienced experimenters. There are no expensive components in the circuit, and the circuitry could hardly be any more simple than it is. If this circuit can be scaled up to operate as a household heater, it would mean that electrical heating costs could be reduced to a tiny fraction of what they are at the present time. That sort of cost reduction would make a major difference to a very large number of people, which makes this circuit very interesting indeed. The operating methods which are used in this style of circuitry are described in considerable detail in the patent application WO99/38247, which has been filed for this system. Reading those descriptions can be helpful, so here is a digest part of that patent. And there is where the patent starts. covering the field of invention, background of the invention, the various details and discussion of the operation, and a brief description of the drawings themselves. There are a number of drawings in the actual arrangement itself, and the section of the patent which is reproduced there you should find fairly interesting. The document continues after the extract from the patent, and it continues with some descriptions which I have put in to demonstrate how the circuit examination has been performed and what the features are, the test results which are worked out, and the various details on the operation itself. There are quite a large number of pages in this document, so the details which are there are worth taking a look at. There is a disclaimer, however. It says it must be understood that this document is presented for information purposes only and must not be construed as being an encouragement to either build or experiment with this or any other circuit. The people who have investigated, designed, built, or described this circuitry are in no way liable for any loss or damage caused by your actions, should you decide to experiment with this or any other circuit. Should you choose to do that, the responsibility for your actions rests entirely with you alone. This document, while presented in good faith, does not warrant that all attempted replications of the circuits described in it will definitely perform in the same way as those which were investigated during the tests which form the basis for this description.